Welcome back. This particular video will finish up our pre-chapter or a review chapter, whatever you want to look at it as. So this will be the end of the review, and starting with the next video, you're going to see us go over new material. Really good chance you've seen it before, but it's not considered review for this class. All right, so we are looking at radicals. We're going to see lots of square roots, lots of cube roots, and all that good stuff. The first thing that we need to talk about is simplifying each expression by removing as many factors as possible from under the radical. So problems 1 through 22, they're going to give us problems that don't necessarily come out quite as pretty as we'd like. So the first one I want to look at is number 4, the square root of 50. The problem with the square root of 50 is that 50 is not a perfect square. So there's nothing I can multiply by itself to get 50. So what I want to do is I'm going to attempt to break this down to numbers that I can take square roots of. So if I think about 50, I've got 5 times 10, which doesn't help me because neither one of those are perfect squares. What else we got? Ooh, 2 times 25. So I can change 50 to be 2 times 25. If you have a problem with perfect squares or perfect cubes, I strongly suggest that you sit down and just write you out a list of your perfect squares. Like, 1's a perfect square, 4's a perfect square, 9, so on. Just make you a list so you've got something to look at and kind of really drive this home what your perfect squares are. Okay, so we've got the square root of 2 times 25. 2 is not a perfect square, so I'm going to leave it underneath the square root. 25, however, is a perfect square, so the square root of 25 is 5, and it comes on the outside. So anytime you take the root, it comes out front. Let me go over some words here with you. This is a square root. Anytime you don't see a number here, I'm like down here, where's it at? Here, this has got a 3 on it. If you don't see a number, you automatically assume it's a square root. We just don't put a 2. It's kind of redundant. This thing under here is called the radicand. So if you hear me use that word, that means it's the stuff underneath it. The 2 or the 3 here, that's called the index. That just tells us what we're looking at. Okay, so that's that problem. Let's move on. I'm going to look at something that's got variables in it. Typically when you see things that have variables in it, it makes it harder. With radicals, it's actually easier to work with the variables, I think. So we're going to do number 6. It's the square root of 32y to the 5th. 32, of course, is not a perfect square. So if I think about perfect squares in 32, we've got 132 doesn't help. 2 and 16, which does help because 16 is a perfect square. So we're going to do 2 times 16. And with these exponents, I can make them really easy or I can make them really hard. One of the ways you can make them really hard is you can say, oh, if I think about perfect squares and y to the 5th, I could change, I just need an even number. So I could change y to the 5th to be y to the 4th times y, right? Because y to the 4th times y will give me y to the 5th. And then we go through and we take our square root, and we're going to say, okay, I can't take the square root of 2. It stays under. I can take the square root of 16. It's a 4. I can take the square root of y to the 4th. That's a y squared, because y squared times y squared is y to the 4th. And I cannot take the square root of a y, so it stays under. Again, guys, I personally think that's the hard way to do this. Now, if that makes more sense to you, have at it, do it that way. I think the easier way is to come back up here and say, okay, remember, if you don't show anything here, you assume your index is 2. So what I'm going to do is I'm going to take this 2 that I have right here, and I'm going to divide it into 5. So how many times does 2 go into 5 evenly? Well, 2 goes into 5 evenly 2 times with 1 left over. So there you go. It's just a quick division. Whatever's left over goes back underneath the radical. whatever you got comes out. Done. Let's do another one. We'll come back to that idea. I want to do number 8. So I want to look at a multiplication problem. We've got the square root of 2 times the square root of 32. Again, like with most of math, you do have a couple of options on what you're allowed to do here. When you're multiplying radicals, to be able to multiply radicals, you do have to have the same index. So in other words, you can do a square root times a square root or a cube root times a cube root. You, however, cannot do a square root times a cube root. It doesn't work. You've got to try something different for that. So I am allowed to multiply these. I encourage you, multiply these before you try to clean up. I know 32, the square root of 32, we just did. You could change that to be 2 on, or 4 on the square root of 2. However, I'm going to encourage you not to do it that way because you're making the problem harder on yourself. When I have a multiplication problem, I'm going to go ahead and multiply. So the square root of 2 times the square root of 32 is going to be the square root of 64. And then, of course, the benefit to doing that is the square root of 64 is 8. I just made the problem so much simpler on myself. So that one's the square root of, or excuse me, 8. All right, that's multiplication. You multiply as long as they have the same index and just clean up what you get afterwards. Let's look at an addition and subtraction problem. So I'm going to do number 12. So number 12, I've got 3 on the square root of 28 minus 4 on the square root of 63 plus the square root of 112. Okay, to add or subtract radicals, you have to have the same index, meaning square root, cube root, whatever, and you also have to have the same radicand. Remember, radicand is the number that's underneath your root. So my radicand for my first radical is 28. My radicand for my second one is 63. And my radicand for my third one is 112. None of these are the same. So right now, I can't do anything with this problem. So what I'm going to do is I'm going to use that simplification technique that we used for number 4. I'm going to try to clean these radicals up, because I do think there are perfect squares hidden in each one of these numbers. Okay, so if we think about 28, with 28, we've got 2 and 14, 3 won't go, 4 and 7. Ooh, I like 4 and 7 because 4 is a perfect square. I need to take this back. All right. I'll clean it up in a second. 63. How about 7 times 9? And then plus square root of 112. 112. How about, let's do 16 times 7. That'll give us 112, and 16 is a perfect square. Okay. Now, this is the first problem where we've seen numbers on the outside and we're bringing numbers out too. So on this first one, I've got 3. The square root of 4 is 2. Anything that comes out from underneath this radical, like the 4 is going to come out as a 2, is going to get multiplied against whatever's already out there. So I'm going to have 3 times 2 on the square root of 7, because 7 is not a perfect square, minus 4 times, I can't take the square root of 7, but I can take the square root of 9, which is 3. And then plus square root of 16 is 4. We got the 7 underneath, it's still stuck there. Let's clean up what we've got. So 3 times 2 is 6. So I've got 6 on the square root of 7, minus 12 on the square root of 7, plus 4 on the square root of 7. Okay, we are getting somewhere. We do have the same radicand for every single radical here. What that means is I can combine my like terms. So I can combine everything together. When we combine stuff, it's the numbers on the outside that get combined. It's no different than if you had like 6x minus 12x plus 4x. It'd be 6 minus 12 plus 4, then you just stick an x with it. Same thing here. So 6 minus 12 is negative 6, and negative 6 plus 4 is negative 2, and that's just on the square root of 7. The square root of 7 is along for the ride. All right, cool. Let's look at, let's do number 18. So number 18, we have the fourth root of x to the 8th, y to the 7th, z to the 11th. Okay, I could say here and try to change. Now, x to the 8th is fine because, you know, 8's a perfect fourth there. The 7, y to the 7 and z to the 11th, I have to work on. So I could change y to the 7th to be y to the 4th times y to the 3rd. And I could change z to the 11th to be z to the 8th, z to the 3rd. Again, I think that's the hard way to attack these problems. I think the easier way to do it is this. My index is 4, so I'm just going to take 4 and divide it into each one of these exponents. So how many times does 4 go into 8 evenly? Well, 4 goes into 8 evenly 2 times. So I'm going to have an x squared on the outside. Because it went evenly, you're not going to have any x's left underneath the radical. Okay? How many times does 4 go into 7 evenly? Well, 4 goes into 7 1 time evenly with 3 left over. So I'm going to have a y cubed on the inside. So I've got a y to the 1. And again, you don't need the 1 on the outside. I'm putting there so we can follow. Okay? Still one more time. How many times does 4 go into 11 evenly? So 4 goes into 11 evenly twice. So I'm going to have a z squared, so that gives me 8. And I need 3 more z's. So I'm going to have x squared, y to the 1, z to the, ooh, that's a 2. That's an ugly 2, but it's a 2. Z squared, and then the fourth root of y cubed, z cubed. Again, I can't do anything with the y cubed, z cubed on the inside of that radical because they're different bases. I'm stuck with it. That it is what it is. All right, let's look at, oh man, let's do 22. 22 looks cool. Number 22. They give me the square root of b cubed times the fourth root of b cubed. Okay, it's a multiplication problem, which is great, except for the fact, remember, to be able to multiply, you have to have the same index. I have a square root and I have a fourth root. That is not the same index. That means to me that my radical rules don't work for this problem. So if my radical rules don't work for this problem, where do I go? I say let's go back to what we learned in a previous video. So when you can't do what the current section says to do, try something from previous sections. I can rewrite the square root of b cubed to be b raised to the 3/2. And the reason I can, remember, the nth root of a to the m is equivalent to a to the m over n. Okay? I can write the fourth root of b cubed to be b raised to the 3/4. So instead of using radicals, I've switched to exponents. Does that help us? And yes, it does, because you have the same base. So because I've got the same base and I'm multiplying, I know that when I'm multiplying by the same base, I can add my exponents. So I'm going to add 3/2 plus 3/4. And if you do 3/2 plus 3/4, you get b to the 9/4. So I couldn't do that with radicals, but I can do it with exponents. Okay, now here's the thing about this. Because my problem started with radicals and they want me to write my answer as radicals, this b to the 9/4 is not going to cut it. I've got to rewrite it as a radical. And I'm going to, once I rewrite it as radical, I may be able to clean it up then. So using this rule again, I'm just working backwards this time. B to the 9/4 is actually the 4th root of b to the 9th. Now, I know that I can clean this up because my index is smaller than my exponent that I have underneath the radical. So how many times does 4 go into 9 evenly? 4 goes into 9 evenly twice. That'll put me up to 8, so I'm going to have 1b left over. And after all of that, like forward and backward work, this is what we end up getting as our final answer. B squared on the 4th root of b. Cool. Let's look at, let's do number 24. 24 is different. So number 24, the directions ask us to simplify each root if possible. Okay. As we have already learned, you can't split up plus and minus signs. So addition or subtraction operations, you're stuck with them. So I can't go in here and say, oh, the square root of 9y squared is 3y. I can't do the square root of 30y, so I'm just going to leave it, and then the square root of 25 is 5. Nope, it does not work that way. So I need to try something to where I can put this in terms of exponents. The only thing that I can think of doing is factoring. So if I go through and factor 9y squared plus 30y plus 25, using the AC method, if I go through that whole process, or you can use the perfect square trinomial rules, that's completely up to you. But if I do go through that process and factor, this is what I end up getting. Now, why is 3y plus 5 times 3y plus 5 helpful? Well, that doesn't look like a 5 at all, does it? So why is that helpful? Well, the reason that's helpful is when you have two 3y plus 5s, you can actually write it like this. So really, it doesn't matter what you've got in the parentheses, it's the fact that it's a square. So the square root of a square basically just cancels itself out. So the square root of 3y plus 5 squared is just 3y plus 5. Now, I do need to put that 3y plus 5 in absolute value marks. And the reason that is because it come out from underneath an even root. When you have even roots, you cannot have negatives underneath your roots because that leads to imaginary numbers. And as I've said multiple times throughout these videos, we are not dealing with imaginary numbers. So you need to make sure that whoever looks at this knows I can't have negative numbers. So what the absolute value bars do for me is, like, let's say, for instance, somebody worked this problem, they wanted to figure out why. So they've got more information than we do. And they go through and they solve y out to be, I don't know, -2. So if you plug -2 back into this thing, you get 3 times -2 is -6. -6 plus 5 is -1. When you try to take the square root of -1, that comes out as an imaginary number. That's bad for us. So by putting the absolute value bars on this says, okay, when I get the -1, if I take the absolute value of -1, I get +1, and I can take the square root of +1. So it's just a way to clean up our answer. Guys, that's not the case with odd exponents or odd indices. So if you had a cubed root or a 5th root, you wouldn't have to worry about the absolute values because you can take the cube root of a negative. All right. I'm going to do one more problem from this section, just so you've seen it. We're not going to do a whole lot with this. The last problem I'm going to do is number 30, which is rationalizing the denominator. Rationalizing the denominator was something that was a lot more important before calculators come along. Because our technology has advanced so much from the time that math was being created, you know, we don't really have to rationalize the denominator because our calculators can think without having it rationalized. Rationalizing the denominator was very handy for when you didn't have a calculator and you had to do everything by hand. It made the math a lot easier. So the way that rationalizing the denominator works, it just means that you want to get the radical off the bottom. So you don't want to have a radical on the bottom. You want it to go away. So I need to multiply by something that's going to make the square root of 8 become a perfect square. Well, to make the square root of 8 become a perfect square, I need to multiply it by 8, but that 8 also needs to be under a square root, because that's the only way that the radicands get multiplied together is if they're both underneath the radical. And then to make sure I'm not changing the value, just the appearance, if I multiply the bottom by the square root of 8, I need to multiply the top by the square root of 8. So I'm multiplying by 1. So on top, I get 4 over this, or 4 on the square root of 8, and then on the bottom, I now have the square root of 64. Now, the nice thing about the square root of 64 is the square root of 64 is 8. And because there's no addition or subtraction in this problem, it's really straightforward, really nice. I can reduce the 4 and the 8 to be a 1 and a 2. So my final answer here is the square root of 8 over 2. The square root of 8 over 2 is the very same fraction as 4 over square root of 8. And if I had a lot of math to do without a calculator, the square root of 8 over 2 would be a lot nicer than doing 4 over the square root of 8. So just a quick little blip there. Like I said, we're not going to do much with that. I just wanted you to see it. But there it is, rationalizing the denominator. And that wraps up our review chapter. So the next video is going to go over chapter 1. And I'll see you then.